Welcome back to the Enclosure Institute once again. As I'm sure you know by now, I'm Phil Taylor.
And I'm Jimmy Budd. Today we'll tackle the topic of reliability testing and the value it can bring to your design.
Imagine an enclosure that contains the sensors, monitors, and transmitters that observe, record, and communicate the water level and quality of water in a large community's reservoir. This equipment would be subject to seasonal temperature swings, UV exposure, rain and wind, and anything else Mother Nature decided to throw at it. If the enclosure's seal were compromised and the internal devices malfunctioned or shut down altogether, a number of dangerous situations might threaten the community's water supply. The situation might not only be dangerous, it would probably be expensive. And it might not only be expensive and time-consuming to fix or replace the device, but also expensive to correct the conditions in the reservoir that went awry when the electronics malfunctioned.
Predicting failure is the focus of the design engineer and the quality engineer. Wouldn't it be great if every device could be tested in every actual condition for the length of the time that the device is expected to perform? It's obviously impractical, but there are a number of reliability tests that can help engineers predict. Reliability testing for a gasket is the process of evaluating how well a gasket performs under various conditions over time. Reliability tests simulate real-world stressors such as temperature fluctuations, pressure cycles, mechanical loads, and chemical exposures, just to name a few. Today we'll look at some of the common tests for gasket reliability. We've briefly mentioned most of these before, but they deserve some more discussion here.
Compression set testing measures how well a gasket returns to shape after being compressed. In the test ASTM D3574 or ASTM D1056, materials are compressed 50% of their original thickness and held compressed for a specified length of time at a prescribed temperature. The engineer can also apply other conditions to the test environment that mimic their application environment. These ASTM tests also allow for accelerated heat aging, which simulates the test conditions for a longer time period. As we explained in previous videos, at the end of the compression and hold period, the foam is allowed to relax for a short time and then its thickness is measured again. A reliable gasket material will return to within at least 5% of its original thickness.
Next, let's talk about testing for stress relaxation. As we mentioned previously, ASTM D6147 and ISO 3384 are good tests that evaluate how the sealing force of a foam material will degrade over time. As a gasket material is compressed, the foam pushes back against the sealing surfaces with a measurable amount of pressure. Over time, as the foam experiences compression set, the amount of pressure the foam is able to apply is relaxing. These tests define the amount of compression, such as 25%, and the temperature of the test environment, such as 70 degrees. Then the amount of pressure being applied by the gasket material is continuously measured over time. During the test, the conditions that the material sees while under compression can be varied, including temperature and humidity. For long-term reliable sealing, the engineer will want a foam material that retains as much of the original compression force as possible.
Thermal cycling can be an added condition applied to a gasket material to help simulate conditions like those that will be experienced in the ultimate application. For example, material can be exposed to cycling temperatures and humidity conditions in a test chamber for a period of time and then put through an ASTM test for compression set or stress relaxation.
Chemical resistance testing is used to determine the gasket's durability when exposed to various liquids or gases. Typically, materials are exposed to chemicals of interest that might be seen in the expected applications for the device. In most cases, the percentage of reduction of the material's tensile strength is used as a predictor of deterioration. Foam gasket materials aren't typically used in situations where tensile stress is applied, but tensile strength is generally the first material property to degrade and is used in these cases as a bellwether property.
Finally, remember the IP testing and rating system for ingress protection that we discussed in previous sessions. These test conditions subject the enclosure to atmospheric conditions that are predicted for the actual environment in which the device will be used. If you remember, the IP rating system is a two-digit number. The first digit describes the allowable ingress of solid matter. IP5X allows a small amount of dust to penetrate the enclosure, but not enough to interfere with the function of the enclosed devices. IP6X, on the other hand, requires that the device is dust-tight.
The second digit in the rating system addresses the device's ability to seal out moisture under various conditions, from dripping water to powerful water jets and all the way to submersion for up to several hours. You may know the IP rating your device must pass based on the industry or service application where you intend it to be used. Certainly, compliance to industry standards and regulations are good reasons to perform reliability testings, but there's other reasons too.
Testing helps the engineer to validate design. Reliability testing can confirm good design choices or alert the team to potential weaknesses that can be strengthened before product launch.
Thorough testing can help to prevent downtime and unscheduled maintenance. Emergency repairs are costly and never a welcome event.
Testing can ensure safety. In industries like aerospace, chemical processing, or nuclear energy, gasket failure can result in catastrophic outcomes. Testing ensures performance under the worst-case scenarios.
In short, reliability testing of the enclosure's gasket ensures confidence in sealing performance, which is essential for safety, efficiency, and regulatory compliance across many industries.
Well, that about wraps it up for today, Jimmy. We look forward to seeing you guys next time at the Marion and Rogers Enclosure Institute. Till then, I'm Phil Taylor.
I'm Jimmy Budd. Thanks for watching.